We're being asked to set up an integral in spherical coordinates of the volume inside a cone, above a hemisphere, and below a plane. I'm just going to start drawing from left to right and to see what happens. I'm going to draw a cone first, about like that. I guess I can make it go up a little bit. There's my cone. Yay! It says, I want the part of the cone that's above a hemisphere. So what I'm going to do is draw a hemisphere that sort of looks like this. You notice they're both starting at the origin. And then below a plane. Well, okay, how about if we make this the plane? I actually already have the important part drawn. Yes. So what we want is the part of that's above this, below this, and inside this. So what we have is this chunk in here. That is what we want. Now, in order to start setting up an integral in spherical coordinates, what we should always do is make sure we have integral, integral, integral. We're just finding volumes, so we just need rho squared sine phi. We usually find the rows first, so I'm going to put a little d rho here. And I start drawing rays. So I'm drawing rays. Drawing rays, 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 drawing rays. Now, in order to find the limits of integration of rho, I need to know what is rho as those rays enter the region. Well, they're all entering the region as they hit the sphere. They're all leaving the region as they hit the plane. Now, in spherical coordinates, the equation of a sphere is really easy. This is a sphere of radius 4, and so the equation is just going to be literally, it even feels like radius is 4. So this is a 4, which is great. We know the equation of the plane up here is z equals 5. Now, we don't want to know what z is, we want to know what rho is. So we know that z is equal to rho cosine phi, like that. And we have to solve for rho. So rho is going to be 5 dividing by cosine phi. I'm going to write secant phi only because it gives me a little more room. So I'm going to come down here and put 5 secant phi, like that. And we've taken care of the rho part. I know there's also going to be a d phi. And I want to know what phis I was using as I was drawing all those rays. Well, here's a couple rays that didn't hit the region, 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 right? In fact, is the lowest phi can possibly be is right here. And so what we need to know is what is phi, which is this angle right in here. At that point. Now, you can see that we had to include the ray that shot straight up, so we had to include the angle phi equals 0. That's not bad. In order to find the angle of phi over this, we almost always have to start with the equation of the cone. Now, the equation of the cone we have is z equals 2 square root of x squared plus y squared. And remember, with spherical, even though r is not part of the spherical coordinate system, it gets used in a lot of calculations, like so. Z is rho cosine phi. This is 2r, and r is rho sine phi. So this is going to be 2 rho sine phi like this. So I'm going to deal with this part of the equation and this part of the equation like this. I can cancel a rho. I can divide both sides by cosine, divide both sides by 2, and I'm going to get 1/2 is equal to the tangent of phi at the crucial angle I want. I'm solving for phi, and I'm going to get phi is equal to the inverse tangent of 1/2. I don't want an estimate for that. I want the exact thing, so I'm actually going to put in the inverse tangent of 1/2 like that. And the only thing I need to do now is ask myself what thetas I was using as I was drawing all those rays. Well, usually when I'm filling a cone, I usually think as I'm filling this cone with straws. I actually had to walk my little head all the way around, and that's what's going to tell me that the theta I'm going to use is going to go from 0 to 2 pi. So there's our integral. The integral from 0 to 2 pi, the integral from 0 to the arctangent of a half, the integral from 4 to 5 secant theta of our basic volume of a spherical block. And that's it.